So what we are going to do here is work on something called linear programming. And in years past when I've taught this, I've pulled up this email that I'm about to show you. And to be honest with you, I'm not 100% sure how much it helped. In fact, when you use it on the other classes, Mr. Borg, did you really go into it much in detail?
I did it even less so in third hour, and then fifth hour just didn't do it.
Just didn't do it. So
Actually, no, I think I just looked at it and like showed them you're gonna have inequalities, and then a graph looks like this, and then vertices. But that was about it. So like a minute.
Yeah, so I don't think we even need to do it with these guys. I don't think so. So, spot decision. Let's just not. As we kind of go through this, you're going to start to see some examples. Today's going to be more of just a lecture day. I'm going to give you maybe like one problem for homework, and we are going to do a Collins paper for homework actually, based on your standard form graphs. Okay, I'll get to that later on today. But for now, just kind of, this is not really my style. I'm not really a lecturer. It's more of, if you haven't noticed already, a give and take, like what do you guys think is going to happen next and so on. This is just going to be kind of just soak all this information in. And I apologize because it's going to be the whole hour. Okay. Linear programming, that's what this whole chapter is about. What does linear mean? What does the word linear mean?
Line.
A line, right? So this is real world applications of of graphing, basically. And a lot of it is used in the business world. For instance, trying to determine your profit margin versus how much you're going to spend. Okay? So in other words, like if you're a store, if you're any local convenience store, you have to buy stuff from the supplier and then you sell it for a little more than what you bought it for, right? You guys understand that concept at least? And so where is your break-even point? Where is it where I buy this and however much I sell will break even and then I'll make all profit from there? And that's the kind of things that this is. It's going to be graphing for that. So it's real-world application. Okay? Linear programming itself is a technique that finds the maximum, and I'm just going to shorten that to max, and or minimum min values for two quantities at a time. So more times than not, we're looking for the maximum. That's not always the case because the minimum, I don't want a minimum profit. I don't want to make a little bit of money. I want to make as much money as I possibly can, right? So most of the times it is for the maximum, but it could, there are going to be problems you're going to see where I'm asking for the min as well. Most of those types of problems aren't the story problem type problems. They're the just go try and graph them and figure it out. And those I think you'll find fairly simple. The objective function is basically the function we are trying to maximize / minimize relating the two quantities. This is often profit, okay? Often about profit. And you'll see it in a lot of these problems. I think there's one problem on a homework assignment where it's about calorie consumption, or actually calorie distribution based on running and walking, how much you lose and stuff. But most of the time it's about profit. Okay. So you'll see an example in a few minutes, but basically it'll say P equals, and then it'll be how much money are we making, like $3 for this and $4 for this, etc. Okay. Your constraints, oh, by the way, this is all vocabulary. You guys remember the vocab test in geometry? How many of you love vocab tests? No?
Well, no,
It probably did help some of your grades if you could remember which is which. No vocabulary test ever in algebra 2.
Are you sure?
Positive. Been teaching this for a few years. So yes, I'm positive. What I'm doing here is just so that you guys recognize the vocabulary, we talk about it, and I'm going to use these words as we go forward, but you're not going to get tested on this, okay? On the vocab itself, that is. Constraints are the limits. What What does it mean to constrain somebody? Constrain somebody?
Hold them back.
To hold them back. And that's what constraints are in this too. They are basically, we can't go past this amount, you know? So they are the limits, holding it back, on the variables in the objective function. They are the limits based on what we can do, okay? Now the feasible region, you know how to do. You've done this actually. That inequality sheet that you just did. Remember what the solution was on those inequalities? What did the solution look like on those inequalities that I had to graph that were due today? Do you remember what the solution was?
Double shaded.
The double shaded region, right? You guys remember that? Where it was double shaded, that was the solution. Well, that's essentially what the feasible region is, except for it's going to be more than one. It's going to be more than two. It's going to be 3 or 4. Okay. So the feasible region is the area closed by the constraints. And you might be saying, what? So let's put in parentheses. The multi-shaded region. Okay. It's where they all overlap. Okay. And you're going to see we're going to have more than just 2 inequalities for a lot of these problems, but some of them are just obvious. Okay, we'll get to that later too. Vertices. Vertices are points where the constraints cross, otherwise known as points of intersection. So remember we did 6.1, that graphing assignment, that where you had to actually find the point of intersection. That's the same kind of thing I'm talking about. We did 6.2, 6.3, where you had to solve it using either elimination or substitution. That's the kind of thing I'm talking about. It's the points where the graphs cross. And the majority of the time, the overwhelming majority of the time, you'll be able to just look at your graph as long as you use a straight edge. This is critically important that you use either your ID or a ruler or something like that to make sure your graphs are as accurate as possible so that you can see the points real easy. Okay? Now there's ways to do it without, which we'll get to. But let's talk about this future problem. By future problem, I mean tomorrow. We have an example here where, like I said before, a distributor, some kind of store, is selling cases of mixed nuts and roasted peanuts. You can order no more than 500 total cans and packages. That means big bulk packages of these cans or these packages. And then you have no more than $600 to spend. Again, you have a budget. You don't want to go over. Plus, you know if you go over it, you're not going to make that money back, so you don't want to go over that. How can you maximize your profit, and how much is the maximum profit? And so they have it up here. It talks about how you buy a case, you know what I mean, like a case, you think even a case of pop, right? Well, a case of these mixed nuts, there's can. It's 4 by 3. There's 12 cans per case of mixed nuts. And for roasted peanuts, there's 20 packages per case. So I don't know if they're stacked or if it's just a smaller container, but you only get 20 packages per case. What you pay as the store owner is $24 per case for the mixed nuts and $15 per case for the roasted peanuts. But then you sell them for $3.50 a piece and $1.50 a piece. So what ends up happening is, well, $3.50 times 12 is $42. So basically I paid $24 for this case. I'm going to make $42 off this case. So that's where they get the $18 profit. Same thing here. I paid $15 for the case. I'm selling for $1.50, so I'm going to sell it for $30 total, which means I'm going to make $15 profit off of that case. And imagine after the course of maybe a year, you buy these cases once a month, just on roasted peanuts, you're going to make $180, okay, profit off of just that. All right, so we'll come back to that problem. Let's talk about the steps. There are 3 specific steps, and some of these steps have more than one thing involved with them. What I'm going to do here is I'm going to just tell you the step, and then we're going to draw an example down below. And the example that I'm going to talk about is dealing with chairs and tables. Okay? If I know that I have to make this many chairs and this many tables, actually, Holland is really worldwide known for our furniture distribution. Can you guys name the furniture places in Highland? Hayworth, Herman Miller, huge ones, right? Howard Miller, I think, is another one. I know that Trendway does it. Donnelly, which I think is called Magna now. They're another one. Some of your parents probably work at some of these places, right? I know my stepdad worked at Herman Miller all growing up. So huge, widely known. So if we talk about, first of all, step one is to develop the variables and write the objective function. Develop variables and write objective function and constraints. Okay, so what I'm going to do down here is I'm going to actually extend these lines all the way down, both of these, because right below it I'm going to give you an example. And again, we're not going to solve this example. I'm coming up with this example literally off the top of my head, so it's not something that's like, okay, this is just showing you what the problems, what I'm talking about, what the steps are, what we're trying to do. So in my example, we're going to call X tables and Y chairs. Okay. So this is my first step, right here. I develop the variables. Okay. Now I have to write my objective function, and again, my objective function is based on profit. And what I'm here to tell you is the chairs, for every table, I sell, I make $18 profit. For every chair I sell, I make $15 profit. In other words, how much it cost me to make the table, I now sell it and make $18 more off of that table than what I spent to make it. Okay? So what happens here is, we've got, let me kind of separate this here. We get a profit, which is going to be 18 per chair, plus 15, or 18 per table, plus 15 per chair. So this is called the objective function. And what you'll notice is, and what you're going to see later, is there's a lot of inequalities in this with the graph and shade, graph and shade. But for this, the objective function is always in equals. And we never ever graph that. I don't know if you want to write yourself a little note. We never graph the objective function. This is the thing we plug into later for positives and negatives. Again, I know a lot of this isn't making a whole lot of sense yet, but it will. Yes, ma'am?
What do the parentheses?
It says OBJ function, objective function. I was just abbreviating it.
And then what does
The first one says develop variables. So I'm just kind of taking each one of these steps. So this step has kind of, I guess if we wanted to, this kind of has an A, a B, and a C right here, I guess. Well, let me zoom this a little bit. Yep. Now, the last part is again the constraints. And the constraints are, well, maybe I have, in terms of hours, I have 2 hours that it takes for a table, and 3 hours that it takes for a chair, and combined, I can't spend more than 60 hours a week on it. So I have a constraint. I know it takes 2 hours for a chair, I know it takes, 2 hours for a table, I keep doing that, 3 hours for a chair, and combined I only have 60 hours of manpower to be able to devote to that. Similarly, there might be something else about how much it costs for each part of something. Maybe it costs like $1 per chair, plus $4 per table. I did it again. And I only have $30 to spend. I'm totally just coming up with that off the top of my head. But I just want to show you what the constraints look like. And the other part, and you're going to see this a lot, you're going to see x is greater than or equal to 0, and y is greater than or equal to 0. So again, the chairs is greater than or equal to 0, and the tables is greater than or equal to 0. Why wouldn't I deal with negative numbers? Why would I say they're all greater than or equal to 0? In this problem, anybody have an idea? Yeah, what do you think?
You're never not going to have a chair?
I'm never not going to, well, I could possibly not have a chair, but I'm never going to have negative chairs, right? Even if I break it, it was a table or a chair that was there, I just broke it, right? It's not like it was a negative chair. We're not putting chairs back in the ground or something like that. I don't know how to even say that. But anyways, that's why. That's exactly right. It's just positive. We're not going to have negative of something that's an object. All right, there's step one. This, by the way, is called our constraints. Constraints. And what you will see, you know what, I'm going to do this, I haven't done this before. So those are called our constraints. Go back up to constraints, up above, that third definition there, constraints, and let's write in parentheses here, inequalities. Graph and shape. Inequalities, graph and shape. Because that's what our constraints are all the time. They are inequalities that we are going to graph and shape. Yeah. And a lot of it is going to go back to standard form type graphs. That's why we did that first, then we did inequality second. We're kind of putting them both together in this chapter. All right, step 2. Step 2 is to graph the constraints. So I'll put in parentheses here, inequalities. I'm just, again, abbreviating that, Storana, so you see that. Inequalities. We're going to graph those to determine feasible region so, and actually there's more to it. So from this, once we graph it, from this, find vertices. Remember we talked about vertices are just the corners, the points of intersection, created by constraints. And sometimes you may have to use elimination or substitution. So again, in order to sometimes get the points of intersection, if we can't just see it, we might have to actually solve using points, elimination or substitution like we've done before. Okay. So here's what I mean. Again, the graph is going to not really be based on this. I just want you to see what it looks like. Do an x and a y axis, but you're going to stay in the first quadrant. So something like this. And I'm going to use 2 different colors here just so you can see it. You don't have to right now. In fact, you don't have to at all, ever, but it sometimes helps you see it. Okay? And I said that with the inequalities before. And so all I'm going to do here is just going to draw a straight line like this. See if you can get it as close to what I have as possible, because I'm intentionally doing another one here to there. Now there's shading involved with this, and the overwhelming majority of the time the shading is towards 0, 0, because I'm talking about restrictions that I can't go over something. And so like for the red one, I'm going to shade kind of inward like this. And for the pencil line, I'm going to also do the same thing. And so you'll see the feasible region is the double shaded region. All of this. I'll give you a second to kind of catch up with me. But what you will see is I did not color this because it was bounded by the red line there and the black line there, so I didn't do this little triangle in here. That's not double shaded. It's cut off by the red line. So now I've done graph the constraints to determine the feasible region. The feasible region, again, is that double shaded region. Okay? And from there, I need to find the vertices. So this is the graph, of course. The vertices are right here. Maybe put a dot where those 2 lines intersect. Right here, where the x-axis intersects that line. Right here, where the y-axis intersects that line. And at 0, 0. And I put these dots really big intentionally so that you see, well, I'm going to put it right here too, dot equals vertices. So again, the dots are just where they intersect at all of these points. Okay? The corners of the feasible region. And I'm going to label these. I'd like you to as well, just so you can see what's going on. This we're just going to call 0, 5. This we're going to call 6, 2. This we're going to call 8, 0. And this, of course, is 0, 0. When I give you problems to do like this, I will give you graphs, gridded pictures, so you can see it really easy. You don't have to try to guess. Okay? Any questions so far? Kind of weird because we haven't really seen this before, but we've been leading kind of intentionally up to this point where we've graphed, we've done points of intersection, etc. Okay? Anything else? Questions? Okay, let's just keep going. Step 3 is to test, and by test I mean plug in the vertices to find the max/min for the objective function. So, earlier, I said that the objective function, obj, fn, cn, objective function, was p equals 18x plus 15y. And so what we're going to do, and oftentimes I'll have a chart for you, is we are going to plug in each one of those points. We're going to plug in 0, 5. We're going to plug in 0, 0. It doesn't matter the order in which you write these, by the way. 6, 2, and 8, 0. And again, when I say plug in, I mean plug in x into x and y into y. Okay? So I'm going to kind of go through and show you that work real quick. This will be 18 times 0 plus 15 times 5, which I will just tell you is 0 plus 75, which is 75. That you can use calculators for, obviously. As I keep going, obviously this will be 18 times 0 plus 15 times 0, which is just 0. That would obviously be my minimum, which makes sense. If I don't sell any chairs or any tables, I don't make any money. Then I've got 18 times 6 plus 15 times 2, which is 30 plus 108, which is 138. And then the last thing is 18 times 8 plus 15 times 0, which is 144. What's the maximum? 144, right? Maximum means the base, right? Excuse me. So, our maximum, if I go back to like what the question is asking here, would be, right down at the bottom if you have room, or even right above it, 8 tables, 0 chairs at $144. That would be, after all that work, what I'm looking for as the answer. Okay. This will make, again, more sense as we go. Ready for something easier? Next page. So, on the next page, we have examples of what it is I'm talking about with all this crazy stuff. And in these, we don't have to determine anything. The variables are already preset for me, x and y. Okay? The constraints are already preset for me. Y is greater than, y is less than, etc. Okay? Now, then I have to graph it. Let me ask you this, before I even look at the first two lines. X is greater than or equal to 0, y is greater than or equal to 0. Where am I going to keep all of my points for this?
0.
Which quadrant? You know what I'm talking about when I say that?
The
The
second.
top right. Because in here, think of what x is greater than or equal to 0. X is greater than 0, all that way, right? Y is greater than 0, all that way. So everything we do, almost every single problem we're going to do, is just going to be in this first quadrant. Okay. Now, in the rest of these, as we go forward, I'm intentionally just giving you like a blank graph for you to fill in. But I want you to realize that we're not really going to look at any of these. Like, look at the problem right below. All I give you is the first quadrant. Okay. because again, we're dealing with all positive values. Now, let's go graph these lines. These are lines that I hope that you know how to graph by now, but I'm going to do this with you anyway. Where do I start this first inequality? -3. So I go down to -3. And I know it's in a quadrant where I said it couldn't be, but that's okay. We're not going to deal with solutions there, but our graph still would have to start there. And then what do I do from -3?
3.
Up 3, right 2. Thank you for using the word right. Up 3, right 2, up 3, right 2, up 3, right 2. You don't have to do more points. For me, it sure works out nice when I do because it's just keeping my graph consistent. Use your straight edge. Right now, it's not the end of the world if you don't have a straight edge on you. Maybe use the corner of a folder or something like that. And I'm just going to connect my dots. And again, you want to be as accurate as possible. So make sure you don't just rush through it. Really try and line up all your points and draw that line. You'll notice it's solid because, of course, it's greater than or equal to. Remember we talked about it takes more ink to draw that point. So we have that. Okay. Now what? What do I do with all inequalities though? What do you just get done doing on all those graphs? In other words, Friday, what do we do with all those graphs? We graph a line and then we shape, right? We still have to do that. And I don't want to do more than one at a time. Let's just graph this and then shade it. Okay, let's shade it. Notice I didn't go further down this way because I don't care about anything that way. I know, well remember what we did is we said we plug in this point, 0, 0. If I plug in 0, 0, I get 0 is greater than or equal to 0 minus 3, which is -3. Is that true? Yes, that is true. So I'm going to take the blue line and I'm going to shade it up. And I'm not going to be too dark because I got other stuff coming in here that I want you to be able to see. Nothing really that new yet, right? I mean, we've still done this. Okay. Let's go graph the other line. So I got y is less than or equal to -x plus 7. So of course I start at positive 7 on the y. We always start on the y-axis first. And then what does that -x mean again? Right, -1 over 1 too to make it even better, right? So -1 over 1, maybe we could just do that there. And I'm going to, from this point, go down 1, right 1. Down 1, right 1. Down 1, right 1. Down 1. Oh, look, there's my point of intersection. That's kind of nice. And connect my dots. And then, of course, we shape. I'll give you guys a sec to catch up with me. Unless you think you know how to shade it, go ahead and shade it, if you can remember. Anybody figure it out? Am I shading above the line or below the line? Below? Let's check it out. If I plug in 0, I get 0 is less than or equal to 7. And that is also a true statement. So indeed, 0, 0 has to be part of the solution. So for the red line, I'm shading here. Now, for the other two, I don't really need to necessarily graph them. All that is saying again, and again, you don't have to do this, but I'm going to do it. When x is greater than or equal to 0, it's all of this. Okay? When y is greater than or equal to 0, it's all of this. And really all I'm concerned with is, if you can't see it, our region that counts. It's bounded here, it's bounded here, it's bounded by that line, and by that line. So this little figure right here is our feasible region. Maybe make that a little darker on your paper as well. All right, so we did step 1. We kind of did step 2. We haven't finished it yet. But step 1 was just find the constraints, the objective function, which again is given in the problem already. Step 2, graph it and find the vertices. Can you see the vertices here? Can you see the points of intersection? Somebody give me one. What's this one? 0, 0. As a matter of fact, I'm not even going to label them here. I'm going to put them right here. 0, 0. I don't have to do a waste. What is this point right here?
0, 2.
Close. 2, 0. Right, x then y. How about this point right here?
4, 3.
4, 3. If you look at your own paper, it should show up as 4, 3. And this top one? 0, 7. The biggest place where I see kids make mistakes is not in the graphing. It's in the points. And it's, you guys have already done it. Some of you said 0, 2. Some of you were probably thinking 7, 0. Remember that if you're going on the x comes first. If you're going on the y comes second. Because that will throw off your answer if you switch those around. Now all I'm doing is plugging them into x and y. Okay. To find my max. And again, it's saying right in the problem, find the maximum. Okay, so I've got 3 times 0 plus 2 times 0. All I'm doing is using the 3 and 2 that are already there and plugging in x and y. I'm going to go 3 times 2 plus 2 times 0. I'm going to go 3 times 4 plus 2 times 3. And I'm going to go 3 times 0 plus 2 times 7. And I'm just going to do the math there to figure out what I like here. You do not have to do this step if you don't want to. If your next step is just telling me it's 0 plus 0, which is 0, that's cool with me. You can do that in your head. Same thing here. If you can just tell me 6 plus 0 is 6, that's cool too. If you can tell me that this is 12 plus 6, which of course is 18, and this is 0 plus 14, which is 14, you can get a good idea of what the maximum is. What is the maximum? 18. What point gives me that maximum? 4, 3. And that's what goes here. What x and y are that maximize it is what goes here. Okay. So your x is 4 and your y is 3. And that maximizes p, matter of fact, at 18. And I do want you to say that too. Okay. Because not only is it the point at which it maximizes it, but we want the value that is our maximum as well. Okay. How many people feel like this isn't that bad? And not the first page with this. Not that bad? Okay, about half of us. We'll get there. Let's look at number 2. And we're not going past number 2 today. Okay, we might start the introduction, but we're not going to do anything crazy past that. Now, what values minimize? When I taught this class in my honors, or this subject in my honors, I didn't tell them this. But minimize means we want the lowest number, right? Not the highest number. And you're going to see why that's important when we get through this. So it gives us our objective function. Again, we don't have to do step 1 because it already gives us our constraints. It gives us our variables and it gives us our objective function. So let's just go graph it. Do we remember how to graph these standard form functions? Anybody tell me how to graph this first line? Go ahead, Mom. Exactly, because we just do the cover-up method, right?